Welcome to our channel. So the next concept is practical transformer on no load condition. What is our second assumption? The second assumption is effect of iron losses in a transformer core is zero. We are considering iron losses in a transformer is not zero. What are the iron losses? There are two types of losses. One is hysteresis loss and another one is eddy current losses. So we already discussed these two. What is the hysteresis loss and eddy current losses? If we take a machine, losses will be present. How the question will be asked in an university examinations? Explain the practical transformer is operating under no load conditions. That is our question. So I am taking a core type of transformer. So again the same story. The core type of transformer has two limbs. And the primary winding is wounded on one limb and the secondary winding is wounded on another limb. Primary means we are giving the supply. Then I mu or Im, this is called the magnetizing component of current. Yes, I mu is called magnetizing component of current. So this magnetizing component of current is required to produce flux. The magnetizing component of current is required to produce the flux, and one more current is required to meet the losses. That is called the watt-full component of current. So watt-full component of current So generally the phasors are represented with capital letter. This is I mu bar and IW bar. So in some of the textbooks it is given as IC bar, and the I mu bar can be written as IM bar. So one current is required to produce a flux and another current is required to meet the losses. That is called the core losses. So now it is the phasor sum of watt-full component of current or active component of current. This is magnetizing component of current or reactive component of current. So if you draw the phasor diagram, so our supply voltage V, the magnetizing component of current and flux both are in same phase. The induced EMFs are lags behind the flux by 90 degrees. So this is the previous phasor diagram. Now one component is added, so that is called the watt-full component of current. So this is capital I mu. So phasors are represented with capital letters, and the IW is in phase component. As the name itself, it is a active component of the current. Means active means the angle between the voltage and the watt-full component of the current is 0 degrees. The angle between the voltage and watt-full component of current is 0 degrees. How can I add these two phasors? By using a parallelogram concept. Draw a line which is parallel to I mu parallel to I mu. From this I mu, draw a line which is parallel to IW. The length of this one is IW. The length of horizontal line is I mu. By adding these two phases, I am getting a resultant current, that is our no load current. The angle between the V and phi naught is called the no load power factor angle. See, the angle between the V and I naught is called the phi naught, where phi naught is called the no load power factor, angle. See, here one triangle is formed. The horizontal component is IW, the vertical component is I mu, and the hypotenuse component is I naught. So I am drawing like this. This is IW, the vertical component is I mu, and the hypotenuse component is I naught. The angle between these two is phi naught. So cos phi naught is equal to IW divided by I naught. So from this I am getting IW is equal to I naught cos phi naught. Sin phi naught is equal to I mu divided by I naught. The I mu is equal to I naught sin phi naught. This component is core loss component. It's a core loss component which is in phase with V1. This is called the reactive component of the current. So that is lagging behind V1 divided by 90 degrees. If you observe, IW is the in phase component and I mu is lagging the supply voltage with 90 degrees. So we have a core loss component that should be equal to, this is called the core loss, V into I naught into cos phi naught. Generally the no load power factor is approximately equal to 75 degrees to 80 degrees, and the no load power factor as this cos phi naught is called the no load power factor is approximately equal to 0.2 lagging. So 0.2 lagging. So if you applied, or if you are represented in a complex form, I naught is equal to IW plus J times of I mu. So from this the magnitude of I naught is equal to IW square plus I mu square. The angle is tan inverse of I mu divided by IW. Okay, this is a core loss component, so we can write it as a W naught also. So W naught is equal to V into the, what is I naught cos phi naught is IW. Okay, this represents the iron loss component. So coming to one problem, simple problem. A 3300 by 220 volts 30 kVA single phase transformer takes a no load current of 1.5 amperes when the low voltage winding is open. Low voltage winding, low voltage winding is open. The iron loss component. So the iron loss component is 0.4 amperes. The iron loss component is 0.4 amperes. Find the no load input power, and the second one is magnetizing component. Magnetizing component, and the third one is power factor of no load current. So this is the problem. A 3300 divided by or by 220, that means E1 is 3300 volts and E2 is 220 volts, 30 kVA. So generally the apparent power is represented with kilovolt ampere, 30 kVA. No load current is I0 is equal to 1.5 amperes and the low voltage winding is open. So if I am drawing the transformer diagram, so this is code type of transformer, and here you can mount the winding, and another winding is also wounded on the another limb, second limb. This is 3300 volts induced EMF. E2 is 220 volts. The iron loss component is 0.4 amperes. The core loss component or IW is equal to 0.4 amperes. Okay, so what is IW is equal to I0 cos phi naught. IW is given as 0.4. The no load current is given as 1.5 amperes into cos phi naught. From this I will get cos phi naught is equal to 0.2667 lagging. Okay, then you can find the sin phi naught by using your calci. You will get 0.96378. So the magnetizing component of current I mu is equal to I0 sin phi naught. The no load current is 1.5 into 0.96378. So I got it as 1.4456 amperes. The where V0 is equal to no load primary voltage. No load primary voltage, that is 3300 volts. It is E1. Then the power P0 core loss component VI0 cos phi naught. So 3300 into the no load current is 1.5, the power factor is 0.2667, and finally I get it as 1320.165 watts. The core loss component is equal to 1320.165 watts for this problem. This is a simple and easiest problem, just if you know the formulas and concept. Thank you. Subscribe my channel, like, share and subscribe. Thank you.